Waves and sound. We're going to look at sinusoidal, transverse, longitudinal waves and a toss-in on scroll waves. You need to be able to tell me what a longitudinal transverse wave is, the difference between a compression or rarefaction, and relate it to crests and troughs. What is the rest line of the wave, particle displacement, all very casual. And as a bonus, distinguish between a sound wave, a wind, and a temperature-based motion of particles. Sinusoidal means like the sine function. That's it. Interestingly, the term sinus means a bend or a fold and appears in words like sinus, obviously, insinuate, if you get my drift, and sinuous, like a bunch of evil mustachios in a row. Vague definitions can cripple your deeper understanding of things. And here are some vague definitions I was exposed to in my life that caused me confusion. First of all, wind is a movement of air. Temperature is a movement of air. Sound is a movement of air. What the physics? If these are all true, then why doesn't wind sing a song? How come sound doesn't warm me up? And why doesn't a hot cup of coffee scream from the motion of the molecules? Now, this is an exaggerated list of bad definitions, but you get things like this that cause confusion. These three definitions do not help at all because they do not distinguish between the three. They are functionally the same definition. So what we have to do is put on our Rodins. Not that Rodin. I'm talking about this Rodin, man the thinker. We need to put on our, I guess it's not really a thinking hat, it's more of a thinking posture. So pretend you're Rodin's man the thinker, and you're at this moment of contemplation. What would you be thinking about? I know what I would be thinking about is how desperately unsanitary it is to be sitting on that rock that way. And I would be well aware that, the surface and what it was touching, that I would go, other people could have done this, and it's cold, and I'm going to have grit when I'm done. So, but we want to think in terms of physics, right? Not in terms of like the juxtaposition of biological material with non-biological material in a highly unsanitary situation. Should at least have the courtesy of bringing a towel. Here's again where you can feel really stupid. Worse than not understanding is misunderstanding. Simple definitions for quick learning are often so vague as to collide with other definitions, and don't count on it being clarified for you. You may have to do this yourself. This is where discoveries happen. This is why I'm doing this particular section. It's when a scientist suddenly goes, hang on a second, and then they find things. So let's start targeting these definitions and see if we can improve them to make a distinction that makes you go, okay, now I see the difference. First of all, there's a verb in there that I hate. Movement. The only time I want you to use that word movement is if it's a bowel movement. Otherwise, not in physics. There is a better verb that can go in there. Wind is the transport of air molecules from point A to point B. And temperature is the vibration of air molecules on the same spot. Unfortunately, sound is also the vibration of air molecules on the same spot. But at least now we have removed one of the confusing couplings of these definitions. Let's keep polishing. Wind is the transport of air molecules over long distances. Now we're a bit better with only 3 words added. Temperature is the random vibration of air molecules, while sound is the organized vibration of air molecules. Now the definitions are taking shape. This is something you could do, and it would make a huge difference on teachers who test definitions. I'm not big on testing definitions. If I were to ask you one, it would be, what is the difference between sound and temperature? I would never say, what is sound? It's always the exploration of the difference, because having definitions in your head doesn't mean you're aware of the true nature of the definition until you can isolate it and explain how it's different from something else. Anyway, the next part you wouldn't be able to do without me because I come pre-armed with this knowledge. If we want to get to more nitty-gritty specifics, temperature, the molecules are running around 10 to the 14th hertz. 10 to the 9th is a billion. 10 to the 12th is a trillion. This is just shy of a quadrillion vibrations per second. And the distance they vibrate is 10 to the minus 11th meters, which is 100 billionth of a meter. So these vibrations are tiny. You're not going to see them. What about sound? Typically, sound is somewhere between 100 and 20,000 hertz in terms of our perception of it. It can go vastly higher if you're a dolphin. And these sound waves are going to be somewhere between 10 to the minus 4 meters. That's a tenth of a millimeter. And 10 to the minus 7th, which is a 10 millionth of a meter. The smallest sound wave at 10 to the minus 7th meter is still 10,000 times larger than the average molecular movement of an air molecule. So we can see now that there's a fundamental difference between these kinds of waves. Sound waves travel at least 300 meters a second, and air molecules at room temperature vibrate at speeds around 500 meters per second. And we'll see later why this does not turn into a wind. Now let's take a look at those wave frequencies and compare them to the size of atoms. A typical oxygen molecule is 60 picometers in diameter. A PM or picometer is a trillionth. So that oxygen molecule would be 60 times 10 to the minus 12th meters across. How tiny is that? Well, let's say your neck is 30 centimeters. We divide it by 60 times 10 to the minus 12, and we get about 5 billion atoms. It would take 5 billion oxygen atoms to string on a 30 centimeter necklace. An oxygen molecule, on the other hand, is 300 picometers in size. Since it's vibrating and rolling and tumbling, I've put that blue larger circle to indicate sort of like you would find it in there, but spinning like a crazed, firefly, fruit fly. You're just not going to see it lined up nice and neat like a set of barbells on the floor. So on this scale, the vibrations of the molecule due to heat are those 3 little circles put around the oxygen molecule zone. So the heat vibrations are very, very tiny. The smallest sound vibration is 100 times bigger than this graph. The graph, not the drawing. It's 100 times bigger than the graph. So oxygen's heat vibrations are microscopic and fast, where the sound vibrations are fairly large little beasties. Amongst the other things that confuses people is why don't hot liquids suddenly decide to move in one direction? Remember, the molecule motion is random. The average spacing between 2 oxygen molecules is about a billionth of a meter, a nanometer, at STP, which is standard temperature and pressure, what you're sitting at right now. So even though these oxygen molecules can move at 500 meters a second due to heat, it's a random motion. And they're not going to get very far because that's roughly the spacing between them compared to their size. There's not a lot of empty space between them, and they are immediately going to strike someone else and go ricocheting off. It would be like attempting to run through a mosh pit. You're just not going to go very far. With sound, like a wave, the motion, the vibration is coordinated, so collisions are reduced. That preamble, other than trying to be specific with your definitions, is utterly not testable, but I just thought as background material for the future, it might be interesting to you, and then in a year or two from now, you see some of this stuff and go, aha, I remember this. Oddly enough, you're quite more likely to remember the stuff that I told you was not testable, because I've removed stress from you and I've said that. Here's a typical transverse wave. It's a wave like on water, or you can do with a rope. The direction of the wave, V wave in blue, and the motion of the particles in the wave itself are 90 degrees apart, and that's why we call it transverse. Oddly enough, the surface of water is not a transverse wave. It does something a little bit more complicated. Now here's an example from a physicist that you'll see credit below and in the next video. that the particles move up and down, but the wave itself is moving to the right. Longitudinal waves, on the other hand, are typically a pressure wave whose displacement and velocity are parallel. This would be like shoving a slinky, pushing it forward like you just jabbed out your fist in a punch, and you create a compression, and this compression starts to travel, but as it goes, it stretches out the slinky in between. So if you keep repeating these pulses, you'll send a pulse called the compression, and then behind it there will be a spread out area of lower density, which we call the rarefaction. So the displacement of the particles is left to right, and the wave is moving to the right. That's why we call it longitudinal, along the length. What's going to cause you confusion is the plot below. What's going to cause you confusion is when we plot these compressions and displacements, and you see this wave appear, but the vertical axis is not displacement, it's density. The wave didn't actually go like off in some sort of crazy bouncy up and down like an insane bat. The sound waves are not coming to you through the air by traveling up and down on these loop-de-loops. This is a plot of the pressure or density of the air at a given spot, because otherwise a compression wave and rarefaction part of the wave would be a nightmare to keep drawing on tests. So understand that when we plot a sound wave like it's a sinusoidal wave, we've changed the vertical axis. It's no longer displacement off the rest line, it's compression or rarefaction off the neutral pressure that you observed before. And I don't think a lot of texts make that quite clear, the transition, and it will trip up the students who are more deeply thinking, actually. You've probably all seen this density of water versus temperature, that water is not the same density at all temperatures. And here's a question I could ask that makes you seem like you actually understood it, but you did not. What is the density of water at 8 degrees centigrade? That'd be an easy question for a teacher to ask. You go 8 degrees, you go up here and you read over, and then some of you just go 0.99980. Others of you literally write out an average underneath and take 10 minutes to answer that it must be 99985. And you know what? Doesn't tell me you understood the graph at all unless I ask 2 more questions. Label the y-axis with the terms fluffiest and compact. And answer at what temperature is water floatiest and sinkiest. Now we're into physics. Guess what most students will do if I say which end of the vertical represents the most compact version of water, the most dense, and which end is the water with the biggest poofiness, that it's swelled to the largest. Well, almost every student will say it's most compact down here and fluffiest up there. But these density values are increasing, so this is heaviest here, this is lightest here. So it's fluffiest on the bottom, densest on the top. Once you point that out to students, they don't bugger it up again. But why do people do this? At nearly 50% or better will carry this one out. It has to do with your brain. Your brain wants to see down as heavier. We're talking about water, so you think heavy things sink, and sinking is down. I think that's what's causing the mental confusion. Numerically, when density values drop, the object is expanding. When the density values increase, the object is getting more compact. But you just want to see with the word water down as sinking. And that causes you to make sort of an eyesight judgment of the graph, not reading it. Similarly, at what temperature is water floatiest and sinkiest? Well, sinkiest would be the highest density, which is right here at 4. And after that, water starts to fluff up again, and its fluffiest temperature seems to be the hotter you get it, which makes sense. You fill a coffee cup full of cold coffee right to the rim, you put it in the microwave, hit the button, and you find the coffee has spilled out. Question 1 does not check whether you understand the graph. Question 2 and 3 are really important if you want to be doing physics. You must understand what the graph is showing you, not just the ability to read off numbers. Back to these longitudinal waves, you can see now with his animation that the wave is tracking to the right, but the particles themselves are just going left, right, and then the wave moves through them. Schlierian photography can capture these density waves in air using a technique that's not terribly complicated. You just got to make a little device, but you can see this if you had a candle or a campfire and the light is shining through it and you see these patterns on the wall. You can see the compression wave right here. It looks like it's a ripple, but it isn't. It's just an area of higher density, and it's triggered as the shock wave goes through the air. Now it's three-dimensional. You're looking at the edge of a sphere. It's spreading out in all directions, but the Schlierian photography kind of like compacts it flat. So you can see these shock waves traveling. Now these are single pulse shock waves, but in one way you could say, oh, the wavelength of this wave here, and measure the gap. Here's another one of a rectangular slug being fired out of a gun. And again, your brain wants to see these as like lifting up towards you, but they're just compressions of the material, of the air. Scroll waves are something entirely different, and they are so different they're not in any textbooks yet. They don't even have a Wikipedia entry, and they're certainly not part of any high school physics, and in fact I doubt you will study them at all, even during a physics degree, because they're still so advanced. And a scroll wave is like when you roll up a piece of paper and you loosen your grip on it and it starts to unwind itself, like the little green drawing. And these scroll waves that can either continue to unwind like a galaxy spiraling, or unwind and retighten again, are turning up everywhere, and they're at the leading edge of research. So we can see scroll waves forming when two black holes are near each other. You can see modeling of wind around an obstacle using scroll waves. And the other two pictures at the bottom and the top right is there's a remarkable amount of research being done on scroll waves as they apply to heart attacks. And when the heart attack originates, a series of scroll waves start to flow through the tissue. So they're looking at the research end, the initiating event of a heart attack, and how the waves that lead to the fatal spasms in the heart are triggered. And scroll waves are currently what is modeling that the best. The cuttlefish is a really cool fish. I'm going to show you a video clip in a minute. And they have all these waves and ripples that swirl across. When we have a crawling sensation on our skin or goosebumps grow, I wonder if they have a wave pattern like these guys. We just can't see it. And since heart attacks fan out like waves, is it possible the dynamics of the cuttlefish's chromatophores, the little color spots, could be similar? You know, has anyone thought, geez, I'm going to study what happens when I poke a cuttlefish in the pattern of colors and see if they spread out at all, like the animal is consciously controlling it, or if they spread out like some sort of, you know, when you see a fly land on a horse and all the muscles on its back start to twist and shake, that it may be just a combined reaction that's more of a reflex and not under control. And they may go, I can tie it to heart attacks.
The lobster proves irresistible for as long as it looks alive. Once it stops moving, the Broad Club seems to lose its motivation.
Clark Kent outfit, and out comes Superman or Super Cuttlefish.
Giant cuttlefish can grow over 3 feet long. Eye to eye, the big males try to outdo each other with the most intimidating body patterns. The smaller females seem unimpressed.
It's usually a very secretive behaviour in lots of other animals, including other cuttlefishes, and you're lucky to even come across breeding aggregations. But to see thousands of them here is just spectacular. And so for several months, they give up the pretense of looking like seaweed or hiding in amongst the sand or the mud, and they go, bugger it, we're just going to look fantastic, and we're going to fight with each other, and we're going to impress females, and they totally ignore us. We can sit in amongst them. They can almost sit on our head, and that's when the best displays come out.
Range. The chromatophores began blinking again, even though they were no longer getting signals from the brain. So what does this mean? Well, what it suggests is that color change might be a bit like breathing is for humans.
Ah, fish! Then there's the flamboyant cuttlefish, which doesn't try to blend in with It just says, why doesn't the world try to blend in with me? You go, little man. Don't go changing for no...
There are a wealth of other types of waves far beyond the curriculum, like oscillons and solitons. Some, like Schrodinger's wave, that represent particles as wave at the atomic level, are currently part of studied physics, but many others are at the edge of modern physics. So an actual electron might be represented by this. This means no matter how worried you are, there is no chance that you'll hit university and go, I want to major in physics. And they're like, oh, they finished yesterday. There's always more cool stuff out there to be discovered. This is the Maxwell-Boltzmann distribution, and it shows your odds of finding a molecule at a specific speed at a specific temperature. 273 Kelvin is 0 degrees centigrade. Kelvin does not say degrees because it's an absolute temperature scale. All you have to do to convert is add 273 to any temperature recorded in Celsius. So if you're feeling really cold on a minus 30 degree day one day, all you have to do is go, yeah, it's 243. Wow, smoking hot. If we take 273 Kelvin, 0 degrees, we can see the most frequent speed is just over 1,000 meters a second for the molecule. But you see the spread? You find them at every single speed possible. They are very uncooperative. There's no chance at all of you finding all the molecules at the same temperature.
I see you shiver with anticipation.
In a substance. If you take the area under the graph, that will tell you the total number as a percentage that you will find between that speed range of 1300 to 1600. This was the beginning sort of quantum physics, where uncertainty dominated the small world, and it was so hated when it came out that Boltzmann himself committed suicide.
People have to be told.
You know I can't let you do that.
Suddenly you discover humanity. Convenient. If you'd cared from the start, none of this would have happened.
I can change almost anything. But I can't change human nature.
Of course you must protect by its new utopia. What's one more body amongst foundations? What are you waiting for?
leaving this galaxy for one a little less complicated.
I thought you said you cared.